Welcome to our presentation of the 2000 level project, Building Augmented Reality Models and Exploring Their Use in Chemistry Education. Allow us to demonstrate a short overview of the vision we've been working towards throughout this project.
Are you struggling to find answers to your chemistry problems, or you struggle to teach them to your students? Perhaps this helps. Or maybe not that much. But wait, what's this? 3D molecules to visualize on your phone? Looks like someone's going to pass after all.
As you have seen previously, augmented reality or AR is a multi-device technology that uses both virtual and physical elements where it superimposes digital content onto the real-world environment. It can be used on smartphones or tablets, shown through an app to produce three-dimensional models where users can easily manipulate and observe them from different perspectives. In chemistry education, the ability to visualize 2D images as 3D molecular structures is a necessary skill that students often struggle to comprehend, and teachers also frequently find it challenging to teach them. Studies have shown how AR is an effective medium for transferring knowledge through spatial presence, which provides chemistry education with an advantage as students can improve their spatial cognition capabilities by visualizing complex molecular concepts interactively. Since AR has a high potential in improving chemistry lessons, our research developed models in accordance to several crucial concepts learned in fundamental chemistry, ranging from the progression of models in molecular orbitals and structures found in general chemistry, to organic and inorganic chemistry such as stereochemistry and point group symmetry. So, the project aims to sample the effectiveness of learning specific concepts in chemistry using AR molecular models and conduct a survey to investigate how students receive these interactive models. Our stages of research started by experimenting and familiarizing with different software for the most compatible ones for each particular AR model, creating a prototype, and then finishing up with a survey.
The process of creating our models started with choosing which molecules we wanted to feature, designing them, and exporting them to Adobe Aero to become three-dimensional AR models. Our 3D models were built to exhibit specific features like bond angles and orbital shapes. Methane was used as a consistent example for the various topics due to its simplicity and prevalence in all three of the chemistry courses we focused on. To begin the process, we started with free-to-use design programs like Avogadro, ChemDraw, and Blender 3.0. After looking at the features and ease of use of each program, as well as the availability of instructive literature and video tutorials, Blender 3.0 was selected to create the 3D models. Blender 3.0 offers an intuitive interface and straightforward working tools, so building compounds did not present many challenges even to inexperienced users like ourselves. Once the model was completed, we exported it to FBX file and zipped it via the website easywyzip.com. The now zipped file was transferred to the Adobe Aero app using AirDrop, as Aero has limited availability on Microsoft and Android products. Once in the Aero app, an AR representation was made and more features were added, such as animations and rotation of the model. This is where the QR code to access the models were generated. For general chemistry, we wanted to show the progression from basic atomic structure to complex theories like VSCPR and hybridization by also covering 2D depictions like in Lewis structure. While a 3D model of methane's Lewis structure was constructed, its purpose was to show the evolution of an atom into a 3D molecule. For this reason, we did not promote its use with AR as heavily as VSCPR and the remaining concepts. A generic element with two valence electrons orbiting at different radii from the central nucleus was constructed to show a Bohr model atom. Creating orbitals started by developing and sharing a file with a fundamental orbit shape, allowing S, P, D, and F orbitals to be constructed consistently between group members. 13 models that convey specific molecular geometry were assembled for VSCPR theory using a combination of Avogadro and Blender 3.0. Visualizing hybrid orbitals is crucial for comprehending molecular geometry, but cannot be effectively conveyed by 2D representations like with Lewis structure. 3D models of SP, SP2, SP3, and SP3D hybridized orbitals, their molecular geometry, and bond angles were created as general models for hybridization. The topic of focus within organic chemistry was stereochemistry. While there are many facets of stereochemistry, we used models of cis and trans isomers to highlight how AR can aid in comprehension. 6 organic molecules were constructed in Blender 3.0 to visualize cis and trans isomers. The opposing isomers were set adjacent to each other for comparison, as we can see here in the example of pentene. Inorganic chemistry and all subsequent specialized chemistry courses beyond it are typically viewed as difficult subjects for students. There are many topics where AR could be used to facilitate learning, but we focused on point group symmetry for the purpose of this study. Methane was once again used and depicts symmetry elements like mirrors or planes. This model was created by selecting and modifying a specific mesh in regards to its shape, size, and transparency in Blender 3.0. Implementing a survey for this study helped us capture the overall attitude of participants towards AR models in chemistry education. The main target group were students and teachers of the Maastricht Science program, though it was not limited here. The researchers allowed anyone with a high school or higher level of experience in chemistry that were willing and able to take the survey to participate. Open-ended questions were used when applicable, and specific AR models selected for comparison of factors like simple versus complex and use of color.
As a result, there were 39 responses overall, where 56.4% of the participants identified themselves as visual learners, while 43.6% are non-visual. The participants were then asked to choose the most helpful models, where the hybridization model was ranked first, and the Vesper theory model followed by the orbital model were ranked as the least helpful. Additionally, the participants were asked to evaluate the potential effectiveness of the usage of AR models in chemistry education, which resulted in the average score of 9 out of 10. They further indicated specific aspects of the models that enable the 3D molecule to appear more helpful. It turns out that the colors have had the highest impact, with 30.8% overall, while simplicity received only 1.9%. An F-test was conducted to determine the equality of the mean values between population of visual and non-visual learners. The results of the F-test showed a higher than critical value, indicating that the inequality of the variance between this population. Furthermore, the values of how helpful the AR models could be in chemistry education between visuals and non-visual learners are not statistically significant according to the t-test.
With colors having the highest impact in increasing the effectiveness of AR 3D models and simplicity being the lowest, this could explain why models like orbital and Vesper theory were ranked the least helpful. Although Vesper theory and hybridization are tightly related concepts, the 3D hybridization model was still ranked the most helpful, as this could be due to the different levels of difficulty of both topics. Hybridized orbitals require more advanced spatial and theoretical knowledge compared to Vesper theory. Therefore, the usage of AR models may appear to be more supportive, mainly in more advanced branches in chemistry, where the ability of spatial imagination becomes more challenging. Furthermore, despite the fact that students find the concept of atomic orbital models already unchallenging, it was the least helpful model not only due to its simple design, but also having a lack of colors. This outcome supports the idea of the significance of color usage in promoting cognitive abilities and memory retention. So, by analyzing the outcome of the survey, improvements for the 3D AR models could also include colors for visual appearance, and additional annotations on the models were appropriate for a better understanding of what is being displayed and adding more clarity. It is also worth noting certain limitations we came across throughout the project, notably programs that were not fully available for every member in the group due to their compatibility for only specific devices. Adobe Aero is the main application for displaying our AR models. However, not all smartphones would be usable for those without the most updated version of the iOS. Implementing simple designs or characteristics to the 3D models was also rather time-consuming due to the complexity of the programs used. And the survey results cannot be generalized due to the limited number of respondents, as there were only 39 participants overall. To conclude, AR has a vast potential in improving future chemistry education. More complex and advanced models could be introduced across different fields of chemistry. For example, cutting-edge software can be developed in classrooms or even for students to study remotely. Textbooks could become more interactive by accommodating AR 3D models on 2D images. And finally, virtual realistic chemistry labs would allow students to train more authentically without any detrimental consequences. So, wrapping up some of our main points, in chemistry, students will most likely to come across exercises that require spatial abilities. And with the emergence of AR technology, AR could potentially be implemented very well in chemistry education to support students in complex topics that require 3D visualization. As we have seen in the survey of our research, most visual and non-visual learners have found our design and developed 3D models very helpful in understanding specific chemistry topics. Despite little to no experience, the group designed and developed valuable AR 3D molecular models that can potentially be integrated in all chemistry education. Overall, though, the project was exciting and fun and has presented students and educators with a new and better approach to learning chemistry. We are all very thrilled and looking forward to seeing how AR will effectively transform our future education. Thank you for your attention, and if you are interested in more information, feel free to ask any questions and request our full research report.
I'm gonna pull up like the lecture slide. This slide, guys, look. This is a perfect slide!
Can you do the howl?
Ow! I have an idea. Oh, I thought I could knock it off. Wait, I'm gonna try that again. No.
That works.
Thumbs up. Do the thumbs up again.